Okay, so first thing I want to do, and this is a very common cybersecurity job interview question that I ask to people. Um, take out a piece of paper. Take out a piece of paper, and I'm gonna have you draw. Yeah. So here's a simple question for everyone. I'm gonna send. That's it. Draw a computer network. That's all you gotta do. Draw a computer network. Yeah, I'll take you. Give you a few minutes. A few minutes to draw one out. So I already did this in two classes. I did it in the in-person security class yesterday afternoon. I also did it with a cybersecurity and cyber warfare class on Tuesday afternoon, or earlier in that day, earlier yesterday. And it was really nice to see whether you're technical, non-technical, doesn't matter what it is. Generally, people got the general idea. There's no right or wrong answer. Yeah, draw a computer network. Yeah, you know, yeah. All right. Anyone got something to show? Put on your post it on your camera. Hold it up to your camera. See what you got. Oh, by the way, it's like, all right, all right. Oh. Okay. We got the spoken wheel. Okay, so far, you know what I love about everyone drawing here? I love everyone drawing. It's simple, no bullshit. It's just lines and it's simple. Just line, shapes. What we got? All right. We've seen that first. I just saw my first sheep of the day. I just saw my first sheep of the day. That's Noah. That's a joke. There's a sheep in yours. Yes, I'm pretty sure that means a cloud.
That was just general internet. I just can't write.
Yeah. So I remembered yesterday in the cybersecurity and cyber warfare, there were a few people that drew sheeps, also known as clouds. And you know what the cloud is? And one student was, and I don't think she's computer science. She said, yeah, the cloud is just someone else's other computer. Point out. I used to have a whole bunch of hacker stickers on my laptop. It's like my other computer is your other, and my other computer is your computer. One of my favorite stickers. Kevin, let me see yours again. There's something I find let me see if my eyes are playing tricks on. There you go. All right, 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 all right. All right. Um, yeah. And there's a couple of reasons why I ask everyone to draw a computer network. Um, Number one, we're gonna cover the basics today. So number two is you're gonna need that drawing later on for today. Okay, you're going to need that drawing for a little bit later today. Okay, so what we're looking for a computer network in this case is something that is not fancy. I mean, people make this into an art contest all the time. We don't want that. Really, at the most basic level, okay, at the most basic level, if you just drew two boxes and a couple of lines, that's fair. That's exactly what I'm going to do today. So why do I want to talk about networks first and foremost? The reason is because we take it for granted. We depend on the network these days. Number one. Number two, that's where all the cool stuff happens, good, bad, and ugly. Number two. But number three, I think the saddest part of them all is, yeah, we take the network for granted, but no one actually knows how networking works. We just take it for granted. They don't know the underlying, they don't know, how a network really works at even the most rudimentary level. And it's that bad in computer science now because when you're in computer science, most programs don't even require, let alone security, many computer science programs don't even touch networks. It's sad. It's really, really sad. But I want to take a step back. So everyone's drawing looks good. Peyton, let me see yours again. Let me see yours again. Ah, you did the many box. Okay, you said the whole bunch of boxes. I see you have the line, the arrows. Okay, so one of the nice things that we can do, we can still do this even on Zoom. I want to take a step back, and Peyton, may I ask you to be to volunteer? We're going to do like a little role play here, if you wouldn't mind.
Okay.
It's a fun one. Ready?
Yep.
So the question that I have to ask you is, you ever used a telephone before?
Yes, I have used a telephone before.
Okay. All right, all right, all right. I just have to make sure because we're getting to a point and yeah, okay, you know, yeah. Mhm. Yeah, the whole idea of giving a phone call to another person these days is becoming what you call a lost art. Okay, now, Peyton, you and I are gonna have a telephone conversation. We're gonna use fictitious phone numbers, of course. Okay. Oh shit. Actually, I'm an idiot because I was just gonna ask you the next question is when you have a phone conversation with someone, and like in this case, between you and me, what do you need for a phone conversation?
You need a phone and you need to
Okay.
know the address of the other person's phone.
Beautiful. Okay, perfect. Absolutely perfect. If you actually want to add a satellite in there for mobile communication, that's just an added bonus. We don't care about that. Okay. So what we're going to do is we're going to have a telephone conversation. So here it is Peyton. My number is 111-111-111. Lois, bam, Family Guy joke. And Peyton, your number is going to be 617 627, actually 617-867-5309. Peyton, that's your number. Okay. So you and I are going to have a telephone conversation, and I am going to be, okay, in this case, I am going to call you. Okay. That's how we go. Now here I am. I'm going to take my phone right here. You can see a phone. And I'm going to dial 617-867-5309.
Hello?
Hey Peyton, how are you?
I'm great. How are you?
Yeah, things are good. You're not in Massachusetts, are you?
No, I'm actually in Hawaii right now.
Whoa, you're not from Massachusetts. You're not coming back to Massachusetts. You're not touching Massachusetts anytime, right?
I am. I'm actually coming back tomorrow.
Yeah. That means we got a snowstorm coming apparently. 2 feet, something like that.
Yep.
Yeah, okay. So, all right. So safe travels. All right. So there you go. That's a telephone conversation. That was a telephone conversation between me and Peyton. Peyton, thank you so much for this. Thank you so much for the demonstration. You may be actually wondering why the hell am I asking Peyton to do a telephone conversation in this thing, in this whole demonstration? It's a lot. So that is a demonstration, an analogy that everyone should know of in real life. You know, telephone conversation, two hardware, have two phones, and also telephone numbers are unique identifier for telephone. Now I want you to ask, imagine if you now take me and Peyton out, take the two human beings out, take the phones out. Actually, the phones actually may need to stay. That may be okay. But imagine instead of having two human beings, me and Peyton having a phone call, what if you actually imagine and replace Peyton and me with not two human beings with phones, but two boxes, two computers. Replace me and Peyton, two human beings, with just two boxes, computer A and computer B. And now the transition is, instead of having two humans talking on a telephone together, what happened if you have two computers trying to talk to each other? Is that possible? Is it possible that computer A can do the to computer B, and computer B answers and say, hello? And then computer A will actually go back and say, yeah, hey, how you doing? That kind of thing, yada, yada, yada. You got that so far? And here's the great thing about that analogy that I just put up. The whole idea, if you had to diagram and draw this on the board, there's not a whole hell of a lot of changes that you need to make. No. A lot of things actually stay the same. The only thing that is really different is just terminology. And of course, instead of having two stick figures, you just draw two nice boxes that Kevin, that you have drawn. Remember, you got two boxes, right? Okay. So what ends up happening is, I'm going to draw this. Now, anyone can actually say I'm a kind of a low-tech kind of a guy. I'm okay with that. That's okay. Yeah, I'm not going to do the high-tech drawing and crap. So if you're going to have to talk about two computers talking to each other instead of two human beings coming with each other, okay, the only thing that you really need to change are two things. Number one, the unique identifiers, and number two, the terminology of na 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 na, hello and hey, how you doing? Okay. Now, in a telephone conversation, there is the idea of a unique identifier for each telephone. Now, is there such a thing as a unique identifier for computers? Not telephone numbers, but they are also known as what? Boom. Oh, whoa, 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 whoa. IP is called, let me spell it out in gory detail. Internet protocol address. Okay, hold on, because I know someone's going to be really anal about this. Version 4. IPv4 address. So in this case, instead of and just pretend that I become computer A, okay? Computer A's IP address is going to be 127.0.0.1, and computer B's IP address is going to be So imagine Peyton becomes computer B. The computer B is going to have an IP address of 128.103.244.118. All right. So how the picture looks like at this point looks like this. Oh, that sucks. Interesting. Hold on. Uno momento, por favor. Background. Here you go. Can you all see? Now it's crystal clear. That's how the diagram should look like right now. Oh boy, what's the difference? That's a great question. What's the difference between IPv4 and IPv6 then? Okay, hold on. I can explain that one. And someone else can actually also chime in. Okay, IPv4. This is how an IPv4 address in terms of format looks like. It's 0 to 255, got 0 to 255, got 0 to 255, got 0 to 255. Okay. So how many possible IP addresses are there? Is there a limit of IP addresses in the IPv4 space? You bet there is. 0.0.0.0 and then up to 255.255.255.255. So you see a problem already. Actually, we have reached a point in our life where the entire IPv4 space has been exhausted. Every single IP address is quote unquote used up. Noah, did I miss anything?
I guess there's natting. And
Okay. So what's an IPv6 address format? Well, one of the things about IPv6 format is supposed to be offer a lot bigger addressing space, a lot more. But how an IPv6 address looks like this. Instead, the IPv6 address size is 128 bits. Now it's going to look like that, and using hexadecimal values. So not only is an IPv6 address a lot longer and uses hexadecimals, okay, it's also a hell of a lot harder to memorize and to talk about off the top of our head. Let's not actually, we're not going to use IPv6 in this course. Traditionally speaking, everyone in the world, we all still know and love IPv4 addresses, whereas the number is between 0 to 255, that's 0 to 255, that's 0 to 255, that's 0 to 255. Now, what's important to know is that there are certain IP addresses that are already what they call reserved, taken. One of them happens to be 127.0.0.1. Do yourselves a favor in your homes or wherever you are. Point a finger at a computer. Can you, okay, actually get better. I'll do a better exercise. Okay, obviously that's a little bit doltish of an exercise because there's one in front of you, because we're all on a virtual thing anyway. But here's the sad thing though. I should have asked this. Point to a computer that is not the computer that you're currently staring at into. That should also, Now, if this was 10 years ago, it would be probably a lot slow. You will probably take a lot slower to point at a device. If you think about that, 10 years, 20 years ago, you certainly were like the number of devices were limited. Now, if you actually just go blindfold yourself and just spin yourself dizzy, and then wherever you land, your finger on, you're probably pointing at a computer. Isn't that sad? All of those things are computational devices. They all have a computer chip in there. And probably some mechanism to network as well too, to be on the internet. Now, I don't care what you point at. I don't care if you're pointing to whether your watch, whether your iPad in front of you, your video game controller, some of them do now after they have their own chip. If you're pointing at your phone, tablet, or whatever, every computational device that is on a network has a very special IP address, better known as 127.0.0.1, also known as itself, also known as loopback, also known as there's no place like home, okay? Now, here's the reason why 127.0.0.1, also known as home, also known as yourself, also known as loopback, is so important. How many of you in real world and real life actually talk to yourselves? We all do. We all do. It's important. Can you imagine life without talking to ourselves? Now, so if you don't, then you probably are dead or have some other problems. I mean, computers, every single computer needs to have a way to talk to itself for diagnostic purposes and other stuff. Same idea. All right. There's also some certain IP addresses that are also reserved. It's like IP addresses that are 10.0 or 172.16 or in the range 192.168. Usually those IP addresses are reserved for internal purposes only. I'll give you a good example. If you are actually connected to, let's say, a home network, okay? When you do ifconfig, your IP address is going to be like 172.16 or 10 dot something or 192.168. Usually these days, your computing device is assigned a IP address locally, but then when it actually communicates to the outside world, okay, the outside world will actually be wherever your router is. Your router is at your internet service provider. It's going to use a real IP address and just relay it to the outside world. Okay. So, wanted to actually say now. Also want to add something else, which is extremely important. Remember in the analogy, the telephone analogy that Peyton and I did, we did hello, hey, how you doing? Remember that? There is now a way that we need to, for that other thing that we need to change is that terminology. We can now formalize that. The is from computer A to computer B is also known as computer B back to A. The hello. Okay. The oh hi. So we got censored again. Okay. Background, none. So now you have this kind of drawing. So far, so good. Sync, ack, and ack. So this is the hello. Oh hey. And then you see a double arrow line, the fourth line. This one right here. The one that the last one on the bottom. This is when computer A and computer B have a network connection. So computer A needs to know the computer IP address of computer B and then send a sync. Yep, absolutely. Absolutely. So computer A needs to know the IP address of computer B, and then, well, you just know. One way is you just know. Computer A needs to know the IP address of computer B and then send a sync request. So one way is you just know the IP address. For example, in this example, 128.103.244.118. But of course, you all know that that is not how the real world works. Well, what do you do in the real world? You don't know IP addresses. When you actually want to go somewhere on the internet, what do you use? Okay, a URL or what? There's something else, something more simpler. How do you actually go to your favorite website? Marcus, take a step back up. Okay, web browser. Okay, Peyton, hold on. Peyton, when you go to your favorite web browser, you go to, what's your favorite website?
Google, probably. Google.
All right, all right, all right, all right. In the real world, all right, all right, all right. So google.com. All right, a good example is google.com. In the real world, if you actually want to go to your favorite website or your favorite, you actually would enter something called domain name. Google.com, Facebook.com, Reddit.com, 4chan.org, doesn't matter. You don't know the IP, you don't need to, you don't memorize IP addresses unless there's like certain computers in the world. What if I told you that every single domain name, google.com, rapid7.com, they all have IP addresses associated with domain names. So in real life, we don't use IP addresses unless you're managing your own servers and stuff. But what you do, Amazon.com. Do you type in Amazon.com or the IP address of Amazon.com? Okay, so you use Amazon.com and not the IP address. All right, so now, before you do the three-way handshake, oh, hold on, before you do the sync, ACK, and ACK process, one of the first things that you do, or that a computer will do is, what's the IP address for Amazon.com, if you want to go there? Or what's the Amazon, okay, if you're actually trying to go to Google.com, Peyton's favorite website, what's the IP address or addresses of Google.com? What will your computer do? Now you can say it, Marcus.
It would ask the DNS server,
Okay, so what's DNS?
domain name service.
Okay. In lay terms, what DNS, domain name servers, domain name system, I got that mixed up. Have anyone ever used something called a telephone book before? What's a telephone book? Just a lookup table. A lookup table of all like domain to IP address. So what happens is your computer will first make a connection. Okay, hey, what's the IP address for Amazon? Or what's the IP address for Google.com? Then they say, okay, and then once you try to connect to one of those phone books, it's like, oh, yeah, for Amazon.com, go to this IP address. Then then the computer would actually go to sync, ACK, and ACK. Now, do you need to know what's the whole point of sync, ACK, and ACK? The whole purpose of computer A talking to computer B by way of this thing called sync, ACK, and ACK, it's called a handshaking process to build a reliable connection between point A and point B. I repeat, the whole purpose of sync, ACK, and ACK between computer A to computer B is to build a reliable connection, something that doesn't like get dropped or anything. I mean, how would you like it if Peyton and I actually were, imagine that telephone conversation where we're actually speaking, and then of course the conversation, like we can't build a relationship. Phone call doesn't happen. Like the only way that Peyton and I can have a telephone call is she actually could say, hello, hello. And I say, hello, oh, hi, how are you? Same idea with two computers trying to talk to each other. Now, do you need to know this whole process of sync, ACK, and ACK on a scale of 1 to 10, where 1 is not important and 10 is really important? This is an 11. For two computers to actually talk to each other, it has to go through sync, ACK, and ACK first, generally speaking. Now, there's one bit of information that I never talked about in the telephone conversation. So remember Peyton and I did that telephone conversation demonstration? But there's one bit of information that we didn't talk about. Usually when we're talking to another human being, it's not important. But when you do a phone call with an institution, like a college or university, or God forbid, a telecommunications company, you get this instead. Peyton, you know what that is? Anyone know what I'm talking about? Anyone want to take a wild guess? When you call up a company, What do you use?
Automated system.
Hmm? Peyton said, is it the extension? Welcome to your most hated telecommunications company. For technical support, press 1. Billing, press 2. New service, press 3. If this is an emergency, press 4. Don't call 911. For everything else, press 5. You've all been through hell before, right? You've been through hell before with that, right? Okay. So the one idea that I did not talk about when I did that demonstration with Peyton is this idea of a telephone extension number. And as Ping actually says, the whole idea of a whole purpose of a telephone extension is really what department that person is in. Or another way to think about it, more importantly, the service that is being offered. Think about it as a person, department, or service that is being offered. Okay? Now, how important is this idea of a telephone extension number for computers talking to each other? And the answer is very, 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 very important. Oh, one thing. I have a question for each and every one of you. You see that remember that diagram I drew of computer A talking to computer B where it's sync, gack, and ack? You know what that whole process is called? Two computers talking to each other, also known as computer networking 101. So a computer networking is really just two computers talking to each other. So let me ask you all a fun question. The question is, right now we've only dealt with a computer network of two computers, computer A and computer B. But in the real world, you have many computers talking to many other computers. Question, what is the world's largest computer network? The world's largest computer network is, what is it? Oh, yes. Okay, by a raise of hand, who thinks, okay, stop right here. By a raise of hand, who thinks that the world's largest computer network is the internet? Who thinks that the world's largest computer network is the WWW or the World Wide Web? Okay. Who's not 100% sure? Okay. Now, I love this question so much. I love this question a lot. And this is why vocabulary becomes very important. Vocabulary becomes extremely important, not only in security, but especially when it comes to technology. The world's largest computer network is internet. The world's largest computer network is the internet. Now, let me explain what that means. Why is it that and not the World Wide Web? And it has everything to do with this idea of telephone extension numbers. See, in telephone land, the idea is called telephone extension numbers. It's just an extension, it's just a number that goes to a particular department, person, or service. In computer land, when two computers are talking to each other, the idea is called port number. Port number go to a particular service. Okay, does anyone know how many port numbers there are? Anyone? Quite a bit. Okay, here is your numbers. Actually, This port numbers range from 0 to 65,535. Now, do you need to know all 65,000 telephone, 65,000 plus port numbers? Of course not. But you do need to know some very common ones. So I'm going to actually say there's a couple of port numbers that are really important to know. I'm going to say 21, 22, 80, 443. For this course, definitely some port numbers that you need to know. 21, 22, 80, 443. Does anyone know what port number 21 is for? Anyone? Okay, interesting. I like Marcus's answer. It's good, but it's not a great one. Noah got it. But what the heck is FTP? Port 21. But Noah actually Marcus actually gets to an important point. Port number 29 is also known as the File Transfer Protocol, FTP. Hopefully, insecure plain text. Port 21, File Transfer Protocol, FTP. It's also woefully insecure. A lot of the web browsers are now trying to put the kibosh on it. Port 22. Now, if you have actually taken a course in computer science at the department, Aaron, I know you have. Okay. Anyone want to take a wild guess what port 22 is? Close. I'll give you that one, Chris. SSH, secure shell, also known as SSH. Example, how many of you, I think, correct me if I'm wrong, Aaron, have you ever done this before? If you actually need to remote access to the Tufts Computer Science Department server or something like SSH, username,
Yeah.
Okay. So when you're using SSH to securely connect to a remote computer, by default, the SSH program will use 22 behind the scene. You don't type in the number 22 at all. SSH will just use 22 by default. You can specify custom ports if you want by, I think, a -P, I think it is, off of my head. Okay. So port 22 is SSH, port 80. What port 80 for? If computer B in this case have port 80 enabled, what does that mean? What port 80? This one's really important. Kevin says okay, the hypertext transfer protocol, HTTP, AKA. Port 80, the hypertext transfer protocol. What that means in lay terms, web, insecure, plain text. Okay, so for those of you who actually said that the internet, that the web is the world's largest computer network, you're so close. The problem in real life is this: the web is predominantly used. We depend on it for everything. That it seems like to be the biggest part. You know, some people think that, oh, the web is like the biggest part of the internet. And it feels like that way. So it is no surprise a lot of people actually say that the web is the internet. The web is the world's largest computer network. I totally don't blame you for thinking of that way. But the internet, what it is a collection of services. Well, you've seen a couple of them here. You've seen file transfer, secure shell, web. Here's another fun one just on the side. What's port 110 in plain English? Does anyone know off the top of their head what port 110 is for? Anyone? Oh shit, I found it. Yeah, Kevin said it, plain English. Top 3, also known as something everyone loves, or hey, email. Okay, so the internet is a collection of services: web, email, secure shell, file transfer. Oh, port 443 is HTTPS. secure web, which is predominantly the web these days. Encrypted. So when you're trying to order something, or God forbid, when you're actually trying to access your own online bank account, you want to use HTTPS, not HTTP. Because HTTP, I think some of you may have heard of this thing. Oh, eavesdropping. You know, in a telephone conversation, what's support for HTTP? 80. Michelle is 80. So here's a fun question for each and every one. Here's another one. One of my favorite port numbers is port 666. Does anyone know what port 666 is for? Yeah, the devil's number. Take a wild guess. Obviously, it does have to do with the devil. Yeah, port 666 actually have to do with the devil. So a lot of you, so there's like a few people that probably know about this. 666, it's actually for the video game Doom, the original Doom. So back in the day, I'm old enough, so yes, I have played that when I was young. So this is port 666 was a Doom server. If 4 people actually want to play a multiplayer Doom, you could connect to the server at port 666 and play multiplayer Doom. Yeah, Doom with port 666. Now, there's a lot of other services I didn't even talk about. I didn't like a lot of other services on the internet. Anyone ever heard of something called printing? Directory services, remote desktop, streaming videos, directory services. Anyone ever heard of something called databases? Yeah, gas tanks. Yeah, they have their own port numbers as well. So you add it all up. That's the internet. The internet is like all those services. The web, what the web is. Think of the web as just a library. The web is just your local library with a card catalog. It's just a collection of content, videos, books, movies, and pictures. Cut the bullshit. What the web really is just a collection of cat pictures and memes. That's it. I'm just gonna go there. The web is just a collection of cat pictures and memes. Sadly, because we love cat pictures and memes so much, yeah, it feels like the biggest part of that. It's like the important part of our life. That's why people think it's like, oh, the web is the internet. Close enough, not so much. Okay. Okay. Anyone have any questions? Anyone have any questions, thoughts? No, you do this for a living, right? Okay. So does each port represents a kind of a service, and each here's the thing about, so each port represents a kind of a service, yes. And each computer had such port. A computer, a single computer like my MacBook, your laptop, your desktop, except for your iOS devices because they're so locked down, a computer can run one to many services and be available online, be available on the internet. Your computer can be used as a web server. Your computer can actually be used for email, as an email server. Anyone remember Hillary Clinton's email server? Okay. Of course, for security purposes and for good reasons, generally speaking, a lot of our personal computers are not used to serve anything out to the world. They'll give information to the world. However, if you want someone to connect to your computer for, let's say, printing a document, you can enable that. All right. So wait a minute, you may be actually confused and everything. Okay, so wait a minute. You have IP address and port numbers. A port is a service. And we've listed a lot of different services so far. HTTP, SSH, FTP, email, video game. That's quite a lot of services, right? So what does that have to do with the handshake? Here's what it has to do. Anytime you try to connect to a remote computer, in this case, computer B at 128.103.244.118. Before, let's say, for example, I want to connect to 128.103.244.118 for web browsing, to get information from web browsing. What has to happen first is a sync, ACK, and ACK, and then the protocol specific stuff for HTTP. When you connect at homework.cs.tufts.edu by way of SSH, the thing that happens first is the sync, ACK, and ACK between your computer and homework.cs.tufts.edu. That happens first. So whatever service you're trying to access on a remote computer, given its IP address, sync, ACK, and ACK generally happens first. A couple of notable exceptions. Anyone ever had Netflix? Netflix and streaming video and audio, actually, there is no handshaking necessary. You just connect, you just point to the IP address of the domain. As Pira said, it's something called UDP. Okay, it just throws information at you. Oh, wait a minute. Whoa. Okay. Hold up for a second. Here I mentioned something called UDP. I mentioned something called port numbers. And also this whole sync, ACK, and ACK. The whole sync, ACK, and ACK process is called the TCP three-way handshake, or just call it a three-way handshake. All right, and this is where the interesting business actually happens. And also my most hated part of this course. There it is. Sync, ACK, and ACK. You've seen this already. The formal definition, the formal thing is called, I'd say everyone calls it a three-way handshake, but formally it's called a TCP three-way handshake. Here I actually mentioned something called UDP. Okay. So here's the problem here. Here I mentioned something called UDP. What the heck is that? I mentioned something called TCP. Now, one of the things that you should actually be asking yourselves is, what the hell are these things called TCP and UDP? Okay. The important thing that you need to know is, out of today, the three-way handshake is really important because predominantly, when you use any service, the handshake happens, sync, ACK, and ACK, predominantly for most services that you use. But under the hood, it's much deeper than that, much deeper than that. All right. Alex, let's go to Alex. Alex, you there?
Yeah, I'm here.
Alex, have you ever mailed something before, like a letter?
I have.
Okay, excellent. When you mail a letter, what's the process like? Like, how do you actually, what do you do when you actually mail a letter?
You need to specify the address and then like get a stamp and fill out a card, or can be postcard or anything, and then
Okay,
drop it off so that
Drop
it
it
can
off
be
where?
transported.
Drop it off at where?
Mailbox.
Okay. All right, that sounds good. Do you ever care about the things like the postal workers or the mail trucks or the airplane or the sorting facilities. Do you ever think about that kind of stuff?
Yeah, when they drop off
You
packages.
do? Oh, okay. Do you ever think about the airplane? That's that's the mail sorting facility in like Wichita, Kansas.
Yeah, when your package is stuck there.
All right, all right, all right. But yeah, generally speaking, a lot of people only
Yeah.
they only care about I mean, they don't think about getting the packet from point A to point B on time. But you get the idea. Okay, but you get the idea. When you mail a letter, you just make, generally speaking, you only care about it just get from point A to point B within 3 days. I don't care what if they use a Pony Express or whatever the fastest Concorde airplane is. I just need to get the damn letter from point A to point B in 3 days. Think about that level of abstraction. There's a lot that actually goes on to get your letter delivered from point A to point B. And a lot of that stuff under the hood, you don't think about. There's a standard process and abstraction that happens. The same thing actually happens in computer land, in computer, between when two computers talk to each other. Okay. Now, this is probably the most confusing part of the course, and for very good reasons. Okay. But really what happens under the hood goes a little bit beyond sing, sync, ack, and knack. It's a little more deeper than that. How do two computers actually really will happen is such a thing called the OSI model. Now there are 7 layers. Okay, so the OSI model. This is called the Open Systems Interconnection Model. What it is it provides, and this is a standard, quote unquote, that allowed hardware to focus on one particular aspect of communications that applies to them and ignore others. In other words, abstraction. So when you're actually trying to go from computer A to computer B, the real deeper version of it is go through 7 layers. At the very highest level of abstraction, which is layer 7, the application layer, all the way down to the physical layer. And then all the way back out to computer B. The only thing that you need to know are really A, there's only 7 layers of this OSI model. B, the only layers that we really care about, especially in this course, are the application layer, transport layer, and network layer. Let me add a little bit of data link too. Presentation layer and session layer is where this whole idea goes off the rails. Okay, so here's a little bit more. I'm showing this again on Thursday of the OSI model. The reason why this is important is just a bunch of abstraction. Here's what each and every layer means. Layer 7 application is the highest level of abstraction. This is where the services that are used for end user application, the stuff that you and I know and use and love, all the services that we just talked about, web, email, file transfer, SSH, they all belong in the application layer. Presentation layer, no one cares about, but it's used for encryption, decryption, and file format. Session layers that actually be established a connection between 2 hosts. Well, the real important thing is this. It's the one that we really got to focus on is the transport and network layers. I'm going to start off with the network layer first. The network layer reads the IP address from the packet. What's the packet? On Twitch tomorrow. The network layer, what it provides is something called the to and from address, also known as source and destination. But it doesn't provide anything about delivery and guaranteed delivery and error handling. That's with the layer number 4, the transport layer. It's responsible for transport protocol and error handling. Also the data payload, port numbers and all that stuff. TCP and UDP are here. TCP stands for the Transmission Control Protocol. UDP is also known as User Datagram Protocol, where there's no handshake. One is faster than the other. Okay? So think of it this way. You ever hear like in Alex's case, your letter, you mentioned a few times the addressing. The to and from address are part of the network layer, but that's it. That's all it gives you. All the network layer, all it gives you is a to and from address. Nothing about reliable delivery, nothing about error handling, no data at all. That's on layer number 4, the transport layer. The pieces of your letter or your mail that you are trying to send, that's in the transport layer. Now, here's when I'm going to add things up together. Usually you don't ever see the term TCP or IP used on its own. Have anyone ever heard of something called TCP IP? You ever seen that before? Usually it's called TCP IP because they have to work in tandem. To and from address. So it's okay. You never ever just throw a blank envelope with to and from address and then mail that out. You never do that, Alex, right? I hope you're not crazy enough to actually send someone a blank envelope, which is like crazy. There got to be some letter and content in there. There's a reason why that you're mailing something. That's where your transport layer comes into play. Data link is the hardware address. The physical layer is the lowest level. It's like the hubs, cables, switch, all the physical stuff. There's another picture of the OSI model. Same idea. But the only thing that you really should care about, 7 layers, OSI model, 7 layers, okay, and all abstraction. Because as part of the model actually goes way the hell off the rails. I'll mention one more thing. If you actually want to have the most easy, a relatively trivial example to actually illustrate how the OSI model actually works, anyone here a Reddit user? Anyone use Reddit? Okay, we all love Reddit. Better than freaking Twitter. This is one of my favorite examples that show you how it really works. Here's a Reddit user. Want to pass note from point A to point B to another point. You've all done this. Reddit user goes to the application layer. Application layer goes to the transport layer. Transport layer goes to the. I told you no one cares about layers 5 and 6. Internet layer goes to link layer. Link layer goes to the physical layer. Now we're actually at the bottom of the river. We'll go now to point B, bring it up to river to the intended recipient. Note goes from physical layer to link layer go to the internet layer go to transport layer goes to application layer. The application layer goes to the other Reddit user that the note was intended for. Now the user actually get to see the note, and there you go. That's the OSI model. That's how the OSI model works. IP address that I've given to you in this class, 192.128.103.244.118, that's on the layer 3 IP. The TCP three-way handshake, sync, ACK, and ACK, that's actually part of layer 4, transmission control protocol, TCP. But the most important thing is that you got to know layers, and you're going to see, okay, the handshake. Okay. So far, so good. All right. What are your questions? Aaron, you got a question? I saw your hand up, or you're just like wavy. Okay. I want to give you a little head start here. Some of you folks may be asking yourself, okay, I get the theory. I get the theory here. I get the three-way handshake. I get the sync ack and ack is a handshake to build a reliable connection between computer A and computer B, wherever that is. I get that. I also now, I actually get the idea of the OSI model, 7 layers and just layers of abstraction. I get that. Those are 2 important points that you got so far, right? You got that? But you may be wondering, the hell? I get the theory, but is there any way I actually can see all this stuff, the OSI model and the handshake all on a computer screen with my very own eyes? Is it possible? Handshake happened, yep. And the answer is, yeah, there is. And on Thursday, tomorrow on Twitch, the primary focus is on how to analyze network traffic, how to actually understand and analyze computer network traffic. So far, the computer network traffic that you all see are the ones on your web browser screen or on Netflix or a streaming video game, whatever it is. But how does that all look under the hood? How does all that data look under the hood? And I want to give you a little head start here. What you want to do is you want to use a program called Wireshark. You want to do something called packet analysis. When you're loading a web page, when you're actually streaming a video or song, hell, even this right now, this class right now on Zoom is all made up of many units of data. Is streaming many streams of data all the time, milliseconds. A 1 bit of data is called a packet. A packet, what it is just an encapsulation of all the layers of the OSI model, all 7 layers. Yes, 1 unit of data contains all the layers of the OSI model. The web page that you load, the streaming video that you actually that you're streaming, like your song from Spotify, it's made up of many network packets. The quality right now of this stream is pretty good, but that's like hundreds of computer network packets all hitting us at one time because we're on high-speed internet. So far, so good. So here's a little quick start. So I'm going to load up a program called Wireshark, platform independent. Wireshark is free and open source, available for any computer system. Can you all see my screen? What we're going to do, one of the very first exercises I do is I want to open up a sample set of network traffic called sample PCAP. What's a PCAP file? Simple.pcap, here it is. A PCAP file is just a file containing many network packets. Where's my chat? This is a very small file. No, it does not have any malware. No, it does not. But what I'm going to do is I'm going to open this up. I'm going to open this file up. This file will have a collection of what you call network packets. Come on, here it is. 715 bytes. There you go. All right, so welcome to Wireshark. Welcome to Packet Analysis 101. Now, we're actually gonna take a look under the hood between the communication between two computers, computer A and computer B. Computer A is 192.168.1.3, and computer B is 192.168.1.8. So in this network packet, in this set of computer network traffic, how many packets are there? Really simple question. All you need to do, look at 1, 2, all you need to do is count the rows on the very first pane. This is a list of all the packets. It's only 1, 2, 3, 4, 5, 6, 7, 8 packets in this simple .pcat. Only 8 of them. This pane right here in Wireshark will actually show how the packet looks like in raw format, binary. If you try to look at this file, that's the simple.pcat file, all it is in binary. If you try to cat it out, it's all in binary. You have your toolbar here in Wireshark here. Oh, in this middle thing, you click on a packet, you click on any packet, I don't care what it is. And you notice that this middle pane will have a drill down. Remember this thing called the OSI model, 7 layers? This middle pane actually breaks down a packet into all the different layers of the OSI model. The full packet, layer 2, layer 3, layer 4. Yeah, you click on the first packet and you can actually see the MAC address, the hardware address of what computer A and computer B are. And you notice anytime I actually highlight something, if I highlight something in the drill down on Wireshark, the location of where that is in the raw packet also gets highlighted as well. Real cool, isn't it? So if I highlight IPv4, you can see in the raw packet in the bottom pane that the highlight changes. That's where your source and destination IP addresses are. And all the TCP information, including payload and flags, remainder of the packet. All right. So far, so good. So far, so good. Really cool. But what's ECN? I don't know. I still haven't, why is TCP so big? It's the way that TCP is defined. But does anyone notice something on the table? The info column. Does anyone notice something? Does anyone make an observation about the info column? The info column is like a preview of what a packet looks like. But does anyone actually notice something, a pattern in the first 3 packets? SYN, ACK. You can see the TCP 3-way handshake between computer A and computer B right here. Sync, ACK. As Peyton said, that's a handshake. And of course, FIN is someone ending the conversation. One more thing. Again, today is a sneak preview of tomorrow, but tomorrow I'm going to get into a lot deeper. So now I see a network traffic. Well, why do you want to record network traffic? You want to record network traffic. What can you do with network traffic? Well, like anything in cybersecurity, anything can be used for good and bad. But if you have access to packets, you can do things like rip out username and passwords that were sent in plain text. You can reconstruct images and pictures and documents that were sent from computer A and computer B. You can actually troubleshoot network devices. List goes on and on and on. So, wait a minute, does that mean that given a network, a set of network traffic, I can reconstruct the conversation that happened between point A and point B? You bet you can. All you need to do at the very rudimentary level is click on any packet, right click, follow TCP stream. I'll repeat. You want to reconstruct a conversation or the series of files and stuff between point A and point B, in this case, 192.168.1.3 and 192.168.1.8. Yeah, click on a packet, highlight it, right click with your mouse, follow TCP stream. And what you will see in this case is, wow, this one pretty doltish. That stream. What, me worry? That's the text. That was a message sent from point A to point B. 192.168.1.3 to 192.168.1.8. All that there is to it. Wait a minute, does that mean I can actually reconstruct video, audio, and all that stuff? Yeah. Using the same technique. But I'll actually do that tomorrow on Twitch. Okay, and that's going to be a lab too, which I will open up tomorrow, which is going to be officially opened up tomorrow. But you can actually, I posted it, I went ahead, I jumped the gun and posted a public version of it, the same thing that's on Canvas, on the cs116.org website already, and you can have fun. How did you get the package in the first place? That is a conversation I want to have now and in 2 weeks. Not in 2 weeks, but next week. So now you know a little bit about networking. You got a nice crash course today on networking 101. Remember that diagram that I asked you to draw in the very first time, for the first thing? I want you to actually put in the chat. Can anyone think of all the dirty, sinful business that you can do now on a computer network, given what you have drawn? In other words, question. When you draw out a network, it's very big. There are many options, many ways to point out what could possibly go wrong in a network. Excuse me. Type it in. Okay. What could go wrong? What evil business can you do? That's another way of looking at the question. Anyone? On your network diagram, tell me what could go wrong. Anyone? Info sent to the wrong place. Yep. Someone can intercept a message. Yep. What is MITM? What is that? Explain in plain English. Yeah, monkey in the middle. Have anyone ever heard of eavesdropping? Eavesdropping, okay. What else? There's one obvious one. It's a really big problem right now. Chris, let me see a drawing again. Malware, virus, yep. Oh, I can't see because of your background, sorry.
Yeah.
Okay, how many nodes are there?
Sorry, it's basically, there's a,
Oh shit, I see it. Cut the middle one out. What happened if you cut the middle one out? That's an easy one.
there was a gateway, so,
What happened if you cut that out? Cut that out. Take it
so
out.
All right.
You take
So
it out, what
there's-
happens? I mean, it's pretty easy, pretty obvious what happens. If you take that out, what happens?
Direct communication between the server and the client.
Okay, can anyone else talk to anyone else? If you take that
Um,
gateway out, can anyone talk to anyone? Mm-mm.
No.
Okay. Take down a computer or what you call the distributed denial of service, DDoS. DDoS, distributed analysis, this denial of service is to take down a computer out of operation, so no one can have access to it, so kill the availability of a computer. This, what does the D means in distributed? That means everyone beating up on one machine. That's what the distributed means. Distributed means not one, not two, but n number of computers beat up on another machine or take it down. Info sent to the wrong place. Someone can intercept a message. Here's an innocuous one. Here's an innocuous one that can be used really for good and bad. What happened if you you take an IP address? Remember that question I asked on lab number 1? There's a question I asked on lab number 1. Where is this IP address? Now you can actually open a whole can of worms. Who's the owner? Who's the face behind this IP address? Where is it located geographically? So basically, you can do something called stalking. Information gathering. Yeah, you can do that. Also, you may be actually, now they're going back to the question, the big question that, who was it that asked it? See, you actually asked, how did I actually get all those that sample.pcap, simple.pcap, or any data in lab number 2? To make a long story short, how I did it, it's one of these techniques. I had to intercept all the network communication on a network. How did I do that? That'll be next week. So next week, the question is, so how did I get all those packets and PCAPs that you're gonna have for lab number 2 next week? Tomorrow, I'm gonna do a lot of packet analysis and Wireshark on Twitch. But the reason why I asked you to do that diagram day 1 today is so you actually have the understanding of how 2 computers talk to each other. Once you know how 2 computers talk to each other, it's the same idea when many computers talk to many other computers. And number 2, and now to start to think about what could you do bad on the network? There, yeah, I stopped the recording.